Okay, good afternoon friends. Welcome to this second session on the topic of theory of beams. In particular, our objective is to arrive at formulas for bending, deflection and stresses on beams. So in the last class, to have a quick recap, we understood what do we mean by beams. We understood how to evaluate whether a structure is a beam or something else, and we had some discussion about the shear force and the bending moment in beams. We also took up a problem wherein we evaluated the bending moment and shear forces in beams. So we will carry forward that discussion, we will continue that discussion and then we will move on to further topics. In the last class we looked at a cantilever beam which is subjected to a point load of this kind P, and we saw that the shear force diagram could be represented in this form. So we will take it up from here in this class. The first thing that we need to decide is, while drawing shear force and bending moment diagram, is to understand what is the sign convention. So here is a word of caution. Sign conventions obviously differ from different books. If you read different books, they will have different sign convention. The one that I am presenting to you is possibly different from the one that you are reading as a textbook in your college. So please beware of the sign convention that you are following. I would advise you to please follow one and only one sign convention, at least in your early days of learning this topic. Don't confuse yourself by looking at different books and different sign conventions. By all means, practice problems from different books, but learn the topic from one book wherein a consistent sign convention is followed. So I will make myself clear as to what sign conventions I am following. So here is the first disclaimer that the sign conventions obviously will differ between books. Please understand and use the sign convention which is comfortable to you. The one that I am proposing is laid out here. The first and the most important part in solving any mechanics problem for that matter is, please choose the coordinate axis and preferably draw it. Okay. So x and y axis, please, when you are given a problem, please draw the x and y axis. In my case, mostly I will have x axis horizontal and y axis vertically upwards. This again is mostly not followed in civil engineering books or strength of materials book. Usually in civil engineering books, the y will be taken downwards because it makes sense, because most of these applications will have a downward force. But in my sign convention, I will choose x and y axis. X is horizontal and it is towards the positive in the right direction from left to right, and y is vertical, it is usually pointing upwards. Okay. Now the loading and displacement along plus y will be positive. That is pretty simple. We know that the axis of the beam will be along the x axis. We have to decide what is the positive displacement and what is the positive load. The positive load as per our convention would be the one which is acting along the positive y axis. So a vertically upward loads in this case will be taken as positive. A vertically downward loads will be taken as negative. Similarly, when the beam deflects upwards, the deformation will be referred to as a positive deflection. When the beam deflects downwards, it will be referred to as a downward deflection. So that is the first aspect which we have to take care. Clockwise applied moments which are applied in the clockwise direction, as we are seeing in our diagram, then that will be taken as positive as per our convention. We will see the advantage of taking this in our formulation as we go along. There is a lot of confusion regarding the shear force and bending moment conventions. You can take any convention, as I just said. There will be differences in convention between different authors. So take any convention, but don't switch between the conventions. That would be disastrous. The one that I am taking is the following. Shear force will tend to cause, the positive shear force will tend to cause counterclockwise rotation on the segment on which it acts. Let me illustrate to you what I mean by this. So let us take our good old beam. Okay. So this is maybe I will draw it better. This is the beam. So as I said, for drawing the shear force or evaluating the shear force at the bending moment, the first step towards is to cut the section. So we will cut the section, but before that we will mark the x and y axis as we just remarked. So if we cut this beam at a section x here, so at a distance x from one end we are cutting it. So we are going to treat this direction as positive because this shear force V will have a tendency to rotate this cut portion in the counterclockwise sense. Okay. So this shear force is taken as positive. Similarly, the shear on the left face, the shear force on the other direction is taken as positive. Similarly, if you take the other half of the beam, the action reaction will dictate that V here is in the other direction. If you look at the V here and let us say the force on the other side, this again will tend to cause a counterclockwise direction. So whether you look at the left half or you look at the right half, the action of V and V alone, do not bring in the bending moment at this point, the action of V is that of causing counterclockwise rotation in the cut portions of the beam. So if the action of shear force on the cut portion of the beam tends to cause counterclockwise rotation, the shear force is positive. Or the other quick way of remembering it is on the right face you should have the shear force in the upward direction, on the left face you should have the shear force in the downward direction. But possibly this rule is more specific and is more unambiguous than up, left, right and up, down, because sometimes you may require to analyze a beam which is the other way around. So I will take this as the defining characteristics of our sign convention as far as shear force is concerned. So shear force is treated as positive if it tends to induce a counterclockwise rotation of this cut segment. So with that, let us return to the presentation material. And for the bending moment, the convention would be as follows. The bending moment will be treated as positive if it tends to bend the segment such that there is a maxima within the segment, not a minima. Okay, it is supposed to be a concave. So convex functions will have a minima, but concave functions will have a maxima. And let me illustrate to you what I mean again through a drawing. So again in this segment, if we try to understand what is happening to the moment equilibrium, so if I take this segment, we understand that there will be a bending moment that is created. So if the bending moment is in this fashion, right, then you can almost imagine that if there is a one dimensional rod and you are trying to bend it in this way in a fashion of a concave function which has a maxima, not a minima. So you can intuitively believe that it will bend in something like this fashion. So if it indeed does, then this is positive. So those sort of bending moments which in fact induce a bending such that the bending is like a concave function, that is taken as per our convention to be positive. Another way of again intuitively qualifying the bending moment sign is the following. Just imagine that on this cut portion you have some gel, split on it. Okay. Now if this beam is particularly flat, then the gel just stays on the flat surface. But if you apply a moment in this fashion, if the bending moment is now taken into consideration, then the question is, will this gel or this watery substance, will it spill over or will it still remain intact on the surface? There can be two cases. If on this surface, on the same surface, if I apply moments in the other direction, okay, if I bend it this way, if I apply bending moment on the same surface in the other direction so that it becomes convex with a minima rather than concave with a maxima, here you can almost imagine that this gel or this watery substance will fall off because the structure itself will deform in this manner. So, it will not be able to hold the water that is lying on top of its surface. Whereas in this case, in the second case, when the beam deflects, it deflects in this fashion, almost like a saucer, like a bowl, and it will still be able to hold the water. So, if the bending moment is such that the bending deflection induced by it is such that it is able to hold water. So, this is a type of loading on the beam which holds water. I mean, this is just a colloquial term, you do not necessarily add water and do this experiment, but it is a thought experiment. If the beam surface, sorry, it will shed water, thank you, this will shed water and the other one will hold water. I wrote it wrong, but I was saying it correctly. So, when you have a beam and the bending moment is such that the water tends to spill over, then we call this that the deformation is such that it is shedding water. Then we call this a type of bending moment as positive. So, this is positive bending moment as per our convention. And the other one is negative bending moment. So, if the bending moment is such that the beam is able to hold the water it contains, then it will be called as a positive bending moment as per our convention. As I said, this convention is not uniform. There are different books which will apply different conventions. So, you are advised to pick up the right convention, whichever one you feel comfortable with, whether mine or yours or any other book, but please adopt that convention uniformly, right. So, even in the assignment problems and the exam problems, if you follow a single convention uniformly, you should not have any problems in getting the final answer. Whichever convention you follow, you will get the same answer. Maybe the sign of the bending moment will change depending upon what you consider positive or what you consider negative, but you must be clear with it. Things like maximum stress, maximum deflection, they will not change. So, that part of it is assured, but please do not flip between conventions, that could be resulting in disastrous. Okay. So, this is about sound convention. Let me just quickly repeat what I said. So, first draw an x and y axis. Next, the deformation which is in the direction of positive y is positive. The loading which is in the direction of positive y is positive. Shear force is positive if it tends to rotate the beam section in a counterclockwise fashion. Bending moment is positive if it tends to deflect the beam in a concave fashion with a maxima rather than a minima. In other words, the bending moment will tend to shed the water, or if you just do a thought experiment with water spilt on the beam and try to think as to what is the direction of the bending such that the water is shed from the surface rather than held on the surface. The direction of the bending moment which tends to shed the water is decided to be positive as per the present convention. You could have the opposite convention also, and that is there in few other books if you read. Okay. So, let us now demonstrate this procedure, calculation procedure, by some simple examples. So, in the last class, let me just using this convention now, let me just firstly repeat the problem that we did in the last class, which was that for shear force and bending moment determination for a cantilever beam with a point load as is shown here. So, here if you see carefully that when you took a cut section of the beam, sorry, before going to the cut section, let us go and find the reactions. So, this was a beam which was having a cantilever or a fixed end at one on the left side. So, we had the first step of solving this problem is to determine the reactions and the moments which are induced at the support. So, we understand that we have to draw a free body diagram of the entire beam in order to accomplish this task. So, towards that end, we understand that if there is an applied load P, there has to be a reaction load P coming at the left end, because only then equilibrium conditions will be satisfied. But then if there is a reaction load P and an applied load P which are separated by a distance L, that means there is a clockwise couple which is induced due to the applied loading and the reaction load. So in order to keep this body in equilibrium, there has to be a reaction moment which will also need to get generated from the support. So therefore the only way to save the day is to induce a reaction moment, the magnitude of which is PL, but the direction of which is counterclockwise, right. So this is the free body diagram of the entire beam, not any cut section. Now if you have to evaluate what is the shear force and bending moment at a particular section X, then what you need to do is to cut it at that section, at that point. And when you cut this beam right here, the first question is what is the free body diagram of this cut section. So again, if you have to apply the equilibrium conditions, you will note that at this cut section there will be a vertically downward force P, right. Now because the reaction load as it is there, which is denoted in black arrows, to balance this upward reaction load there has to be certain load or the acting at the cross section, and this is by definition the shear force, right. So the shear force here is P in the downward direction. Now let us try to evaluate whether this shear force should be positive or negative as per our convention. Now just look at the shear force, don't look at the moments or don't look at the applied loads at all. If you look at just the two shear forces, P which is at the cross section X and the reaction load P, then the effect of this is to create a clockwise moment. So what we had decided as per the sign convention is that the shear force will be positive if it is supposed to create counterclockwise rotation. But here we see the effect of this shear force is to create, about this point it is creating a clockwise rotation. So therefore as per our sign convention this is not positive, this is negative. Accordingly we had drawn the shear force diagram in the negative direction. If you have the opposite sign convention, then this shear force value will remain same, just that this graph will be flipped over, it will be mirror image and then it will be on the other side. But I will rather not try to talk about the opposite sign convention lest it confuses you, but as I said, all sign conventions, if it is properly done, all of them will give you the right answer. The one that I am adopting, I am explaining here. So just to repeat myself, this blue downward arrow is going to tend to deform this cross section in a in a clockwise fashion, not in a counterclockwise fashion, and therefore the effect of this force is a clockwise rotation, therefore this shear force is taken as negative. Similarly, if you evaluate the bending moment in the counterclockwise direction is PL minus X, because the PL part of it balances the reaction moment which is generated at the left support, and the minus Px part of it comes because these two P's, the P due to reaction load shown in black arrow and the P due to the shear force shown by the blue arrow, these together keeps a couple. So if you have to balance that couple also, minus Px in this direction or rather Px in the opposite direction has to be induced. So these two moments will add up to P times L minus X. Look at the direction of the bending moment. The bending moment here is exactly the manner in which we define to be positive. In other words, if you look at the bending moment induced in this cross section, the effect of that bending moment would be to make this part of the cross section concave with a maxima rather than with a minima. In other words, if you imagine that there is something like a watery substance spilled on top of on this top face, then that watery substance will fall off due to this deformation of the bending moment. Due to the deflection induced by the bending moment, it will tend to fall off, and that's why it is positive. It is shedding water, and that's why it is positive, and therefore we get the bending moment to be positive here. It is linear because the expression says so, which we have already argued. So I hope I have been able to convince you regarding the directions and the choice of positive or negative between shear force and bending moment, and accordingly we have been able to draw this shear force and bending moment diagram for the first problem that we did in the previous class. Now we will take up the second problem, which is pretty similar, but now it is a simply supported beam on which there is a uniformly distributed load of intensity W. So as always, the first step is to draw the free body diagram of the entire beam. When you draw the free body diagram, you have to get rid of the supports and replace them with the reaction load. Since these are simple supports, there won't be any moments induced by the simple supports, there will be only a reaction load induced by them. So it is an easy computation to find out that the reactions from the left and right end is precisely WL by 2. So at both left and right support, you will get a reaction load which is equal to the value of WL by 2. Now if you have to understand what is the shear force coming at any cross section, what you have to do is that you have to cut the beam at that section X, and let us see the free body diagram, what happens when the section is cut off at X. So in this case, you have to account for the reaction load WL by 2. There is also a downward load because of this UDL, the value of which is integral W dx, and dx goes from 0 to x. What we have is the following. We have a beam on which there is a UDL acting downwards. The intensity is W per unit length, right? Because this beam has to be in equilibrium, the reactions have to be determined such that the equilibrium condition is satisfied. So if we have to satisfy the equilibrium condition, the conditions are RL plus RR has got to be W times L, and also if I take the moment about this left support, what do I get? I get W the reaction at R is equal to the reaction at L because it is symmetric. You can also verify from the moment diagram, and this will be WL by 2. If you want to calculate the moment about this point, what happens? The moment about this point can be calculated if you simply consider a small element dx of length dx. So the moment due to the small element dx is integral W x dx, right? So there are many such small elements starting from the one at the left end to the one at the right end. So therefore you should take a definite integral from 0 to L. So that sum total of all the moments is going to be W L square by 2 by definition. So what you want is, if I calculate moments about this left support, the moment due to the UDL plus the moment due to the reaction force, which is RR times L, should be 0, which means the moment due to UDL we have already computed as WL square by 2, but it is in the opposite direction as the moment due to RR. So therefore I will put a negative sign here and RR times L, because this moment is acting in opposite direction to the moment induced by the reaction from the right end. So that gives me RR as WL by 2, and from the first equation, if I put this in the first equation, I will get this as a solution. Okay. So then with the reactions determined in the above manner, let us go for the next part of it, that is how do we solve for the shear force and the bending moment of this beam. So we have now cut a section of the beam. So this beam now, this cut section is now of length x. On the left end you still have the reaction load RL, which we have just computed to be WL by 2. The question is, what is the shear force here? So we will denote it by V for now, and we will try and evaluate V. So for that we will have to find RL plus the total load due to this UDL should be equal to V. Now what is the total load due to this UDL over the length x? That is integral W dx 0 to x. Okay. But this comes with, this UDL is directed in the downward direction, and as I said, my sign convention is such that my positive y is in the upward direction. So this W is in fact negative, right. So this minus W dx integral over 0 to x and RL and V, all of them together should be 0, right, which means V of x should be integral W dx 0 to x minus RL, and that comes out as Wx minus WL by 2, right. So that is what I would have written in my slide as the final answer. So Vx, as I have written, my answer is Vx by WL is x by L minus 2, x by L minus 2. This is exactly the, if you take Vx as Wx minus a, so this essentially implies Vx is Wx minus WL by 2, which is what I have derived. Okay. So this is how we calculate the shear forces. In a similar fashion, you can calculate the bending moment by now considering the moment equilibrium of this cut section. Towards that end, what we need to do is again draw a free body diagram. There is an RL force as we have computed. Fortunately, there is no bending, there is no moment at this left end because it is a simply supported, and in a simply supported end you will not get any moments. So it is best that we balance moment about the left support, because in doing so we can get rid of the moment due to the reaction load. But we have to compute the moment due to V. So here again this is the condition, and there will be a bending moment which we take it this way as per our convention. So we need to find out what is this M. So towards that end we first need to find out what is the bending moment due to UDL. So the bending moment due to UDL is integral W, let us take a variable xi d xi 0 to x. Xi is just a variable for integration. The integration limits being 0 to x this time, it is not 0 to L, because this cut section, as I have said few moments back, this cut section is now of length x, right. So W xi d xi from 0 to x is going to induce a clockwise moment. As per our convention, bending moment is also in the same direction, but V is going to induce the opposite direction. The moment due to V will be in the opposite direction as per our picture. So when we take this into account, W is constant, so you will get this as W x square by 2 plus M will be equal to V x, and then you have to replace the value of V which you have already calculated from here. So when you do all that simplification, it will work out that the bending moment is this. Okay, looks a little complicated, but it is not very difficult. So this is how you can calculate the bending moment at this section. So you should not stop simply by looking at the formula, please try and plot it. So what I have done is I have actually plotted it in a computational software. You can plot it even in a very basic software such as Excel. So this is the plot of shear force and bending moment. I could have drawn it in a schematic fashion, but I felt it is wiser to draw the actual plot. So if I just take these expressions and plot in something like Excel or MATLAB or Mathematica, you should be able to see this plot, right. So one thing that we note right away is the fact that the slope of the bending moment, this bending moment diagram is looking like a quadratic curve. It is looking like an x square curve, which is obvious because x square is present here, whereas the shear force curve is looking like a linear curve, and that also makes sense because the shear force expression has a linear dependence on x, right. So therefore it is no surprise that the shear force is linear and the bending moment is quadratic. In fact, the slope of the bending moment curve keeps on increasing. If you go right from 0.5 up to 1, you can very easily verify that the slope of the bending moment curve keeps on increasing, which is what you see in the shear force diagram. The shear force keeps on increasing linearly, the slope of the bending moment diagram also keeps on increasing. This is just an observation at this stage, but a few slides downstream I will be able to show you that this observation is in fact true, and there is a formal proof for this observation. At this stage it is just an observation, but we will establish this more formally, more rigorously as we move ahead. Okay, so now that we have done at least 2 problems for determination of bending moment and shear force, let us, and in that problem till now what we were looking at is that the bending the equilibrium conditions for cut sections of the beam. Now what we will do is we will look at equilibrium of differential element for the beam. So to make matters clear, I will again shift to my tablet. So till now we were taking the beam, we were chopping it off into 2 parts and we were drawing free body diagram of each individual part. Now we won't chop it in 2 parts in this fashion, we would rather try to look at a differential element. So we are now going to scoop out a piece of this beam element, and we are going to look at what is the condition for equilibrium of this small element. So this is an element of differential length dx, which has been taken from a distance of x from some suitable reference. Okay. So with that, let us return back and go to the theory. So this is that small differential element that I was talking about. So this is a small differential element, and as per our conventions, as we said, the right hand side we have to take the shear force in the upward direction, and the left hand side will take it as in the downward direction, because in doing so you are ensuring that this is a counterclockwise rotation, right, that is induced on this piece. Similarly, the direction of the bending moments, which is shown in magenta color, is such that this piece will tend to deflect in a concave fashion with a maxima, or it will shed water, and W dx is quite obvious. So this is the free body diagram of the differential element of the beam. I have used all sorts of colors in these sort of diagrams just to emphasize that each of these forces have different origin. W dx is due to the applied loading which comes to be known from the application that you are considering. The cyan forces, the blue arrows indicate the shear loading, which are in action reaction pair as we have done, and the bending moments are indicated by the magenta arrows. So please note firstly that the choice of all these arrows are as per the sign conventions that we have decided a few moments ago. So let us abide by that sign convention. So the easy thing now to do is the force balance. The force balance gives us W dx is the upward force, V dv is the upward force, but there is a V on the left face which is the downward force. So as a result, the total upward force is W dx plus dv, okay, because the V gets cancelled between the left face and the right face, and you are left with a dv. What is dv? dv is the differential change in the shear force as you go a differential length along the direction of the axis of the beam. So W dx plus dv is equals to 0. This in turn implies dv by dx is minus wx. This w need not be UDL, it can be any distribution of load, right. It can change from point to point, but when you are considering a differential element, obviously within a differential element it is kept constant, because you are really considering a very small piece of that element, and within that small piece of the beam the intensity is supposedly remaining fixed, which is W. But if you take a different element which is located somewhere else along x, then this value will change. So therefore the rate of change of shear force as you go along the beam is minus Wx as per this convention. You may see a different version in different books where dv by dx is is marked as Wx, not minus Wx, but that is simply happening because of different sign conventions, nothing else. You don't get unnecessarily perturbed that why are formulas not matching across different books, or why are formulas not matching between the lecture material and the book that you have. In case you observe that this formula is different only in the sign, then be sure that it has happened only because of a different choice of sign convention. Please, with that understanding, go ahead and resolve the situation for yourself. Now let us go to the moment balance. So we will take moment about the left face. So we will choose a point on the left face somewhere here. The moment due to V plus dV is V plus dV into dx. Similarly, the moment due to W dx, which is supposedly acting at the center of this differential element of length dx, is the intensity of the load is W, which means the force is W times dx, which is upward direction. So W dx into dx by 2, dx by 2 is the moment term. So the total counterclockwise moment is W dx into dx by 2, and similarly V plus dV tends to induce a counterclockwise moment. So V plus dV times dx, the moment term of for this force V plus dV is precisely dx. So V plus dV into dx plus W dx into dx by 2 should be the total clockwise moment. The clockwise moment that is coming from the right face is m plus dm. The clockwise moment that is coming from the from the left face is minus m. The left face in fact has a counterclockwise moment, that is m, right. So therefore they effectively, between these two curved arrows, between these two bending moments indicated in curved magenta arrows, you effectively have a counterclockwise moment only of the value of dm. On the left hand side you have clockwise moments, on the left hand side of this equation you have you have counterclockwise moment, and on the left hand side on the right hand side you have clockwise moments. The effective clockwise moment is m plus dm minus m, which is dm. Okay, that is what I have done. Now if dx is really small, then there is absolutely no need to consider the second order quantities with such as this one, right. So that even this dv dx is a second order quantity, this is a second order quantity. So these two quantities can be cancelled, and what you are left with is v dx is equals to dm. So as dx goes to 0, this is what will happen, and which effectively means that the rate of change of bending moment or the slope of the bending moment diagram is precisely equal to the shear force. This is what we had observed in the previous slide also when we plotted the two graphs, that the slope of the bending moment diagram seems to have a correlation with the shear force value itself. This is the formal proof of it. As I said, these two equations, dm by dx equals to vx or dv by dx equals to minus wx, they come in different avatars in different books in terms of a change in signs. The change in sign happens simply because of the sign conventions adopted in different books. So please be careful when you use the formula and you use the sign convention, be consistent. Don't take the sign convention on one book and take the formula from the other. That will be disastrous. Okay, so the inferences that we have at this stage are as follows. The slope of the bending moment diagram is precisely equals to the shear force at that location, which in turn means the change. So what we have is dm by dx is vx. So now if you integrate between 2 points a to b, then mb minus ma is the value of this integral. So the area of the shear force diagram between 2 points a to b is the jump in moment. So difference in moment between 2 points a and b is precisely equal to the area of the shear force diagram between these 2 points. Similarly, we have the slope of the shear force diagram as the negative of the intensity of the distributed load at that location. So this means again we have a similar interpretation in terms of integral, but to account for the change in sign, this time it is VA minus VB, which is integral W dx from A to B. In the last case we had MB minus MA, which is the integral of the shear force diagram. Now the integral of the intensity, load intensity, is VA minus VB. So with that in mind, both these formulas are very similar. So this is to convince you that these three different loading aspects, the bending moment, the shear force and the load intensity, they are all related. So ideally speaking, you should be able to recover one from the other by taking differentiation or by taking integration as is appropriate. You should be able to recover one parameter from the other at least in an intuitive fashion, that the slope of the bending moment diagram is the shear force and the slope of the shear force diagram is the negative of the load intensity. So these are the inferences that we have at this stage. Okay, there are some special cases which I would like to talk to you through. So in case there is a portion of the beam which is not loaded. So what do I mean by that? We have done this problem a while ago. So let us return back to that cantilever beam with a downward load or an upward load, does not matter. So in this case, in this portion of the beam there was absolutely no load, right. So what we have at this stage, what we have derived is, if you remember just in the last slide, dV by dx is minus W. So let us take this into account, that dV by dx is minus W at x, but in this portion of the beam W is 0. I'll make it better. In this portion of the beam we have W equal to 0, right. So therefore in this portion of the beam dV by dx has got to be 0. That means the slope is 0, the slope is not changing. If the slope does not change, that means in this portion of the beam, in other words VB minus VA has got to be a constant, okay. So there is and this constant is effectively 0, the slope is not changing and you will have the situation as I have marked here. Shear force will be constant. If there is the load which is, if there is a portion of the beam which is not loaded, then the shear force will be constant. So this is just what we had seen. This is exactly what we had seen even in this shear force diagram that we had drawn a while ago. So in this portion of the beam you are seeing that the shear force is not changing. That is because there is no load. If there is a load, then only there will be, if there is a load intensity that is acting here, then only there is a question of changing shear force, which is what we had seen in the second problem. In the second problem we had a load intensity being distributed. So therefore between points you had a change in shear force, but in this case you do not have a change in shear force because W is 0. But if the shear force is constant, that means that bending moment will be linearly increasing, which is again what we saw in the first problem when we took only a point load. Now if the beam is UDL, that means the load is constant, that means the shear force will be linearly increasing. The VB minus VA will show a straight line ascent or descent as the case may be. That in turn will mean that if the shear force is linear, the bending moment will be quadratic. Again, that is something that we have calculated through rigorous formal means. When we did the calculation, that we showed that if the shear force for the UDL was in fact turning out to be linear, this is what we did, the shear force was linear and we found out formally that the bending moment is quadratic, and the graph of it looked like this. And this is now qualified through a formal derivation that this is always true. This is not just true for that specific example. It is always true that when you have a UDL, shear force will increase linearly and bending moment will have a quadratic variation. When there is no load in the portion of the beam, then the shear force is constant and the bending moment will linearly increase. And the next case is more interesting when we have a point load. So till now we were talking about this portion of the beam where there was no load in this red color portion. But now I will shift my attention to this portion of the beam wherein there is a point load, and I will deal with point load by using the concept of delta functions, which I will explain to you in my next slide. So we will firstly consider this a uniformly distributed load of intensity 1 by delta, which is acting over a length of delta, right. So this is quite well defined. Instead of considering uniformly distributed load over the entire length of the beam, I will consider a UDL which is of this kind, which is spread over the region delta, but the intensity of this UDL is here W is equals to 1 by delta, right. Now imagine the situation as delta goes to 0. When delta goes to 0, then you have the case that this UDL is spread within a very narrow region. So therefore it is almost behaving like a concentrated load. What is the total value of the load? The total value of the load is integral W dx, right. So it is the area under this curve. So the way we have defined this function, the area under this function, area under the curve of this distributed load always is 1. 1 by delta times delta is always 1. So therefore this is exactly what we have in mind in the definition of the delta function. So we will firstly consider a UDL of intensity 1 by delta spread over a region of length delta, and then we will take the limit as delta takes to 0. So we will, in the first case we note that the total load that we are defining, total load is integral W dx over the entire range of its definition 0 to delta. So the total load is 1. Now no matter what be the value of delta, small or large, this total load always remains at 1, right. The total load does remain at 1. Now if we take this value of delta to be as small as possible, then in the limiting sense we are approaching the situation of a point load. So point load of unit magnitude, in our understanding that we are proposing at this stage, we are saying point load of unit magnitude is the limiting condition wherein you have UDL of intensity 1 by delta, which is spread over a length of delta. So it is spread over a very infinitesimal region, but the UDL intensity, so as to say, is very large. But despite the UDL intensity being very large, the load is finite. The load is 1. So it is a point load of unit magnitude. If you and this is represented as a function delta of x. So unit point load at the point, let us say x equals to 0, will be delta of x. If you want a point load of magnitude p instead of a unit point load at the same point, you have to just multiply this with p. So p delta x is a point load of magnitude p at x equals to 0. Now instead at x equals to 0, if you want to consider the point load at some different location, let us say x equals to a, then you have to do a shifting. So this shifting is just the argument of this function. Instead of delta at x, it has to be delta at x minus a, right. So p of delta minus a, delta x minus a represents a point load which is located at x equals to a. We are building all this machinery because this will really help us solve problems. These mathematical tools will serve us very effectively when we look at problems involving point load. Now what we must note at this stage is that if you take an integral of this p delta x minus a within any region which just includes this delta function, then we will be getting the value of p. Let me demonstrate what I mean to you. So firstly, I would like to say that if you have a function, let us say something like this, if it is defined as f of x minus a would be just the shifted version of this function by the shift value being a. So if this is f of x, in red I will just try to draw the same function but with a shift of A. So this is just a translated value, you take the function and just translate it. So this function is f of x minus A, right. So now in the next step I would like to use this analogy for delta of x. So we have defined that delta of x is a point load, something which looks like this. So this is delta of x. So if we want to get delta at not at x equals to 0, so this has something happening at x equals to 0, delta at x minus a will be a shifted form of this function, the shift value being exactly equal to a. So delta of x minus a is the one that I am drawing in red. This is x equals to a, right. So this is what I mean by delta of x minus a. Now let us look carefully at as to what is happening for the integration. So let us say this is something like delta of x, which is centered at x equals to 0. If I take this integration between any a and any b, right. So integral of delta x between any a to b, delta as a function of x over dx, okay. If I take from any a to b where a is less than 0 and b is greater than 0, then by construction this is 1. What was the construction? The construction was that the width of it is 1 by delta, the height of it is, sorry, the width of it is delta, the height of it is, so this width was delta and this height is 1 by delta, okay. So the area has to be 1 as long as the integration limits are enclosing the function. If I take an integration limit which does not enclose the function, so if 0 does not belong to the interval a to b, then what will happen? That means I am integrating delta of x between these two limits. Let us say I will call this c and d. If this point 0 does not belong to this interval c to d, then integral c to d delta x dx will be 0, because delta x by definition is 0 outside this, if the interval does not contain 0. So therefore the point is, if the interval of integration contains the center of your delta function, then that integral is going to be 1. If it does not contain the center of your delta function, then that integral is going to be 0. And p times delta x is obviously p instead of 1, that also comes through from the definition. So with that in mind, let us now return to this. So p delta x minus a, if you integrate over an interval which contains the center of the delta function. What is the center of the delta function? That is the point x equals to a. So if you choose a b which is lesser than a and a c which is greater than a, then the integration interval does contain the location of the delta function which is x equals to a. So therefore this integral will give you a value of p. So these are very intuitive ideas of delta function. If you do a more advanced course, you will know many more formulas about delta function, but this is roughly what we will require for delta functions if we wish to use it towards our problems related to beam, okay. So with this, let us now see what happens when a beam is indeed subjected to point load. So this is the type of problem that we have taken up in one of our previous slides, just that I have changed the direction of the load. Instead of a vertically downward load, I am now taking a vertically upward load. So as per our definition, as per our derivation rather, as per our derivation, we have VA minus VB is integral W dx, right. So integral W dx is the change in shear force from the left to the right, right. So what is it that will happen here if we apply this formula to this situation? So this point load, which is now treated as a delta function, is integrated, is firstly centered at x equals to a. So we will have at x equals to a point load, which we will say as P times delta x minus a. The intensity of it is P, I mean the total value of the load is P, and it is centered at x equals to a. Now we take a point which is just on the left of a, and we take a point which is just on the right of a. They are denoted by a minus and a plus. So as per our definition, the jump in shear force between these 2 points a minus and a plus should be equal to the integral of this, and this by definition is P, right. So there is a jump in shear force VA minus VA plus, and this jump has to be positive, which is P. So VA minus has got to be more than VA plus as per this definition. So VA minus is VA plus plus P as per this convention. So the point that I want to drive home at this instance is that whenever you have a point load, you will have a jump in shear force. That is dictated by this rule that we have just now framed. That if you look at a point load, that is nothing but a special case of a distributed load which is like a delta function. And by the theory of integration of such delta functions, it is easy to comprehend that there will be a jump in shear force at the location of the application of such point loads. So this is an easy check that you should do, and this will be very useful for you to derive the shear force diagram when you do the exercise problems, that at each location where there is a point load, there is a jump expected, and the jump value is exactly the value of the shear force, is exactly equal to the value of the applied force, right. So the shear force jump is equals to the value of the applied load. So again you will see different versions of this formula in terms of signs, because the sign conventions is different across different books. So again please use different example problems given in different books judiciously. Don't get confused with the signs, that would be disastrous. Okay, so at the location of the point load there is a jump in shear force, which is the moral of the story here. Now in lots of cases we will get to see that there is not only a single force but different types of loadings are there, both UDL as well as point load. What we have done is we have taken one example which is a UDL, and the other example which was a point load. Now in case you have both of them, in case you have a situation where there is both a uniformly distributed load as well as a point load, then how do we solve them? The idea is very simple. If you have, because of linear system theory, which we will not get through, but the assumption is that everything being linear, you could as well decompose this problem into 2 parts. You could first find out what is the shear force and bending moment due to the point load. You could then find out what is the shear force and bending moment due to the uniformly distributed load, and simply add them up together. This will work as long as situations are linear, and we are assuming in this first course that your beam behaves linearly. Okay, you need to know much more to understand why this assumption is required, and when does this assumption fail, and things like that, which will come up much later in a more advanced course. But in this first level course, it is assumed that your beam is behaving linearly, which essentially means you can divide and rule whenever, if you have to find deformation, if you have to find stresses, if you have to find shear force, if you have to find bending moment, all that you have to do is consider not the entire load but one load at a time, and if you calculate each of these quantities for each of these load cases and then add it up all together, it will work pretty fine. So this is the approach that I will be proposing. So for determine the shear force and bending moment due to each constituent load, add the shear force and bending moment of each constituent load to determine the total shear force and bending moment. This will also work for deformations, as we will see. Okay, so this is the approach of dividing and ruling. So if we have a combined load which is this, we will first do this problem where we take just the point load, derive the shear force, derive the bending moment. We will then do another problem which is considering just the uniformly distributed load, derive the shear force, derive the bending moment, and then we will simply add the two pictures up together or the two expressions up together. So this is the pictorial fashion in which we will do it. Analytically, we could also do it for the first type of loading. We will find that the shear force is constant within this region, which means that the shear force expression works out to be minus P if x is lesser than A and it is 0 elsewhere, which means that in this region, A being the point of application of the load, if the value of x is chosen to be less than A, we get to see a shear force which is minus P, and if x is greater than A, then the value is 0. So therefore the expression for shear force will look something like this. Similarly for the UDL, the expression of shear force looks exactly like this as we have derived a few slides back. Bending moment works out to be this, and I don't want to repeat that part again. So this is the bending moment. On the left hand side what you see is the bending moment due to the point load. On the right hand side you see the bending moment due to the uniformly distributed load. Now all that you have to do to find the total shear force is that simply add these two up, and similarly add the bending moment up to get the total bending moment due to the total load. So this is the approach that you have to adopt. Whenever you have combined loading, please solve the problem one at a time for one loading and then add up the results. It should work beautifully. Okay, before going to the next topic, so by here we are finishing off with our topic on bending moment and shear force. I will take a few minutes, 5 minutes pause at this stage and welcome questions from your side before we move on to the next topic. Okay, KNUMU is asking what is UDL? UDL is uniformly distributed load. Sorry, I think I have not made that very clear. UDL is if Wx is actually constant, then the situation is uniformly distributed load. The loading is said to be uniformly distributed. The loading is referred to as uniformly distributed load. Okay, and it is abbreviated as UDL. I hope that answers your question. This is the undeformed configuration. So this is the point that I am focusing on. It is at a distance of y from the neutral axis. I am trying to find out what is the deformation along the x direction of this point, right? That is my question. So x along the x direction you have a deformation y u, and along the y direction you have the deformation v. So consider a point as shown. This is in the undeformed state. Without application of any load. Now once loading is applied, the neutral axis, I think I made a mistake of drawing it in one color. I will change the color. So this is the neutral axis, as always drawn in red. Once it is deformed, the neutral axis has now become like this, and because of the fact that of Euler-Bernoulli hypothesis, which has to ensure that the blue line and the red line remain perpendicular and the blue line remain straight in this view, the blue line would have gone in this, would have deflected in this fashion. Now we are looking at the topmost point on the blue line. So again we are looking at this, right? So this angle is theta, and we were looking at a, originally this point was just y ahead of the neutral axis. So this distance is y, right? So therefore this distance turns out to be y sin theta. In other words, from its reference configuration to the deformed configuration, the point has moved horizontally by a distance y sin theta. But please note that the point has gone in the negative x direction, it has not gone in the positive x direction. Okay. So the deformation of this point is actually minus y sin theta. So u of this point is minus y sin theta. It has gone in the negative x direction. Rungta is asking me, how can we draw SFD and BMD diagram using divide and rule? Well, I gave you the intuitive feel of it, that the SFD and the BEM bending momentum for the constituent loads are as given in this fashion. So if you have something like a constant low shear force due to one load, and if you have something like a linearly varying shear force due to the other type of load, and you are asked what is the shear force due to the combined load, then it is easy to figure out that the superposition will have a trapezoidal kind of shear force diagram, because if you add a constant graph with a triangle graph, you will get a trapezoid. Okay. So I agree that intuition may fail us if we have to add these two type of load, a linear graph and a quadratic graph. It is difficult to have an intuitive feel for this sort of a loading, but then if you have to truly draw that bending moment diagram, you can always appeal to these equations. These equations are basically the formal equations which, when plotted, would result in these two diagrams for bending moment. So all that you have to do is that once you have got these M1 and M2 expressions out, you have to find M at any section X, which is the sum of these two, M1 and M2, and whatever expression you get, again plot it out using a computational software or things like Microsoft Excel, and when you plot it out, you should be able to see the full bending moment diagram. So that's the approach that I am asking. Yes, I agree with you that in not all cases the intuitive feel will fail us if the situation gets little complicated, but what will not fail us, or what will always work, is these mathematical relations. If you can find an equation for bending moment for one load case, if you can find a bending moment equation for the other load case, add it up, that is the equation for the total load case, and plotting is a simple thing which you should be just able to do it using any software. ACET is asking, is sign convention fixed to define SM, SF and BM? By definition, shear force and bending moment is the reaction forces and the reaction moments which are generated in the cross section. So that part is clear, that is the definition of shear force and bending moment. What you regard as positive shear force and what you regard as a positive bending moment depends on your convention. That positive negative depends on the sign convention. The quantity itself does not have anything to depend on the convention. The quantity itself is well defined. It is only the sign of the quantity which matters. It is just like force. The fact that there is a force is not dependent on the sign convention. Whether you take mg to be positive or mg to be negative, that depends upon the direction of your y-axis. If you choose a y-axis which is vertically upwards, the gravitational force is minus mg. If you take a y-axis which is downwards, then the gravitational force becomes plus mg. So the choice of coordinates decides whether a certain force is positive or negative. Similarly, there are choices which you can make to decide whether your shear force is positive, bending moment is positive, and there are certain choices which I have taken. There are some other choices which are proposed in different books. That is what I wanted to. ACET is asking, in a cantilever, how do we calculate bending moment at every point in the span in case of UDL? I have worked this out for simple support. You can work this out for cantilever also. The approach is just similar. Please take that as an exercise and do it. There is nothing different between a cantilever, UDL and simple support, other than the fact that the reactions, instead of being forces alone, will be moments. So calculate the reaction force, calculate the reaction moment, and then adopt the same procedure to find bending moment as a function of x. If you remember, all my expressions for bending moment and shear force are function of x. So it's just the same approach. It is just that you have to repeat the same procedure now for I think this one, this m2x is precisely the bending moment that I have made the calculation for UDL. So this is the answer, But how I have derived it, I don't want to show it right now because I am running short of time, but you can take that as an exercise. KECAP is asking me why point load has a rectangular shaped graph but why UDL has a triangular shaped graph. I think you are referring to the shear force diagram, that is this one. The shear force for a point load situation, the shear force does not change from this point, which is the left support, to the point of application of the load. That has been reasoned out very elaborately in the talk, that no matter where I cut the cross section, the shear force remains same. The fact that shear force remains same means that the shear force diagram will show something like what you are referring to as rectangle. This essentially means for all the x values from this point to that point, the shear force is just the same at minus p. So that is why it is rectangular. A similar logic, using similar logic, when you calculate shear force at each and every cross section of this beam, which is subjected to a uniformly distributed load of intensity W, you get to see that the shear force now has a linear dependence on x, which is why this plot of the shear force looks like a straight line, and this is what possibly you are referring to as triangle. So the reason why this is triangular and why this is UDL, why this is rectangle, is borne out from the formal derivations. The formal derivations suggest shear force in this case for a point load does not change. The formal arguments, formal derivation suggests that it does change, because dV by dx is W, and dV by dx and W is constant in this case. If the W is constant, then dV by dx, that means the slope of the shear force diagram has to be constant, which means the shear force diagram itself has to be a straight line, right. This is what we have. RTIM is asking shear force and bending moment diagram for uniform UVL. I guess UVL is something like a variable load, but I would like firstly I think I have done 2 examples. I will give many more problems as exercise. There is nothing fundamentally different between different types of distribution of the loadings. So I have given 2 examples to you. I hope that you, using these examples, you should be able to work out any other kinds of problems wherein you have more something like a triangular distributed load, sinusoidal load, whatever you want. The idea is just the same. Take the free body diagram, appeal to equilibrium equations. When you are finding out what is the load due to the distributed load, the effective load due to the distributed loading is integral W dx. The effective moment due to the distributed loading is integral Wx dx. If you keep these factors in mind, you should be able to do any sort of variable loading. I am assuming what you said as UVL means variable loading. I am not exactly aware of this acronym of UVL. I am taking this as a variable distributed loading. So with that, my answer is the approach that I have followed for the 2 problems will be applicable for the variable loading case also. It is just the same. You will do it as a part of the exercise problem that will be posted in the course pack. BITA, you are asking me, when UDL forces are given, why should we take distance from the midpoint for calculating the bending moment? I guess somewhere along I would have made a quick calculation wherein I would have said that the UDL, when you have a uniformly distributed load, let us say W, for calculation of the load it is integral W dx, whatever value comes, let us call this capital W. So this capital W is effectively kept at midpoint. If you don't believe it, just work it out, that the effect, the bending moment that is created because of this W, this distributed load, is same as the bending moment that is created because of this point load. So I can replace these 2 pictures. A UDL of intensity small w will be same as capital W acting at half the length. So why are the 2 same? The 2 are same because firstly the total load is same. Secondly, if you calculate the moment about any point, let us say here, it will work out to be the same. So the total moment of this UDL, which is integral Wx dx 0 to W x dx 0 to L will come out as W L square by 2, right, and integral W dx is W L, and this is by my definition the total load capital W, right, and if this is put at half the length, the moment at the same point now turns out as W L square by 2. So the UDL of W intensity is same in terms of the total load, in terms of the moment, if you replace the effective load by a concentrated load which is at the half the length. So this is just a quick way in which we can do certain calculations. You cannot do it if it is a triangular load or if it is a variable load, right, but sometimes when we are in a hurry, we quickly use this formula for our relation to make some calculations, but I would rather ask the students not to employ these things. Work from first principles, even if it takes a little bit longer. Do from first principles and convince yourself that this sort of things does work out. Okay, KECAP is asking that in case of point load, shear force is constant, but why not bending moment? We know that the rate of change of bending moment dm by dx is shear force. So if shear force is constant, bending moment will not remain constant, because the slope of bending moment is constant, which means the bending moment has to change. So that's exactly why the bending moment takes a linear form, and so therefore if point load shear force is constant, bending moment cannot be constant, because if shear force is constant, bending moment slope, which is equals to shear force, is going to be a non-zero quantity. If the slope of the bending moment curve is going to be non-zero, that means bending moment cannot be constant, it has to be linearly increasing. Okay, JNTU is asking about if any two beams are joined by a link. I don't know what you mean by link here. Why would there be no bending moment at that link point? I think what you are confusing with is not a link but a pivot. If you have a pivot which is connecting two bending moment, the pivot or the pin point does not offer any bending moment, it offers only a reaction. If you have a pin connection between the two, if you have a pin connection between two members, let's say you have a member here and you have another member here and you have a pin connection here. So this pin is supposed to act only as, if you break this piece up, if you break this assembly up into two individual constituents, at the pin you will get only a reaction. At the two constituent elements you won't get a bending moment. That is because the pin is effectively like a roller. What we did what we did for a roller is now true for this pin, which is now connecting the two beams or the two structural elements. So this pin is supposed to enforce the continuity of displacement on the either side. So the displacement at this point, let us say this point is x equals to a. So W at a minus or V, let us say the deformation at the two ends will be the same. This is the condition that the pin will enforce. We have a problem posted for you on this in the course pack. So SVA-CPA is asking what happens when the shear force changes its sign in case of cantilever. If the sign change is abrupt, if there is a jump in the shear force, then it means that there is a point load which has acted exactly at that point. If the sign force is gradual, if the sign change is gradual, if the shear force is turning from positive to negative gradually, then it means there is a uniformly distributed load. Other than that, I cannot think anything more. Okay, we'll come back to the lecture material now and carry on. Okay, so let us now try to understand delicately what is happening as the beam is deforming. So the beam that we are dealing with is technically termed as Euler-Bernoulli beams. This is in contrast to, let's say, higher order beams or Timoshenko beams. The beams that we are dealing with now is technically called Euler-Bernoulli beam. And the hypothesis or the assumptions associated with the Euler-Bernoulli beam is as follows. So if we simply draw a grid of lines in this beam as I have shown in this configuration, let's say the beam before it was loaded, we draw some lines in this fashion. These are rectangular grid of lines, they are perpendicular. As per the Euler-Bernoulli beam hypothesis, as per these assumptions, what we have for sure is the following, that after deformation, this grid of lines will bend in this fashion, but the strange thing is that the perpendicular lines, here we see the blue and red lines are perpendicular. Even after deformation, the perpendicularity is assured. That is, the red and the blue lines before deformation were perpendicular. Even after deformation, the red and the blue lines will remain perpendicular. Also, what you realize is that since this piece of beam is deforming in a convex fashion, it is becoming like a saucer, right? It is becoming like a bowl. So, in such a case, you can intuitively feel that the top fiber is getting compressed and the bottom fiber is getting extended. So, the length of the bottom curve is actually more than the length of this bottom straight line. Similarly, the length of obviously you can realize the length of the bottom fiber in this deformed configuration is more than the length of the top fiber in the deformed configuration, right. So, in turn it turns out that if you now compare between the deformed and the undeformed configuration, the bottom fiber, the bottommost black line which is shown as a straight line in the undeformed configuration and becomes circular, somewhat curvy in the deformed configuration, they obviously do not have the same length. The bottom fiber is extended. Similarly, the top fiber is compressed. This is just a picture, a pictorial fashion. I am trying to bring out a very important result. We will do it in a more theoretical fashion also as we go along, but this is what we refer to as assumptions within the Euler-Bernoulli beam theory. So, when you say that you are employing Euler-Bernoulli beam analysis, it essentially means that you are going to consider all those type of deformations where this assumption is inherent. So, firstly, the deformations are going to be small. You cannot take beams which are bending by large amount. For example, if I take a very flimsy element, I can actually apply a large load and convert this straight beam to something like a quarter circle or even like a semicircle, but such deformations will be very large. Our theory will not be able to accommodate such large deformations. The deformations that we are going to lay down are going to be applicable for small deformation. This is not very restrictive if you look at it from a practical sense also. Remember that our objective is to design structures such that it does not fail. You really do not want to design a structure wherein due to its applied load it bends from being a straight to that being a quarter circle. Much before that you have to make an intervention and make sure that the bridge which was initially straight after the application of a load does not become like a quarter circle. So, bending of a structure to that extent is not permissible in applications. Yes, if you are looking for applications such as forging and other such things where in fact or die casting where you in fact look for large deformation, then this assumption I agree is restrictive. But at present our applications are such that we are looking for to ensure that the deformations are really small, because applications will not run if the deformations are in fact going to be large. So, deformation being small is a very important assumption in our theory. What we have seen here is that the top fiber is getting compressed and the bottom fiber is getting extended, but again a very careful analysis will reveal that the middle fiber, the one which passes through the centroidal axis, technically it is referred to as the neutral axis, that does not change its length. The top fiber in the kind of deformation that is shown in the schematic plot is getting compressed, the bottom fiber is getting extended. So, somewhere in between, which happens to be exactly the centroidal axis, that fiber is neither extended nor compressed, and that fiber is called the neutral axis in the theory of beams. Another very important assumption is that this is the 2D view of it, but you can assume that you have sections or planes which are passing through these blue lines. So, in the undeformed configuration, if you take a plane section which are passing through this blue line and imagine what has happened to this section on the deformed configuration, as per the Euler-Bernoulli beam assumption and as per the Euler-Bernoulli beam hypothesis, we are assuming that these plane sections remain plane, right. You can have, realistically you can have situations where such plane sections before deformation do not remain as plane sections but become a general surface for that matter. But as far as the limitations of Euler-Bernoulli beam analysis goes, we are looking specifically at the type of beams wherein before and after deformations, whatever were the plane normal sections are in the undeformed configuration, they remain as normal sections even as plane sections even after the deformation. This is again a very important analysis feature, and as we see, as we will you may probably see in a higher course, as the thickness of the beam increases, these some of these assumptions do in fact get violated. So that is why we said that this theory is applicable wherein the thickness of the beam is small in comparison to the length. So as I just remarked that the outer fibers are compressed and the inner fibers are, the outer fibers are either compressed or elongated. By outer fibers here what I meant was both the inner fiber on this side and the outer fiber on this side. I should have used the word inner and outer to mean compression and elongation, but I will make that correction. The inner fiber I would say is compressed and the outer fiber is elongated, whereas the neutral axis is unchanged. And similarly the slope of the neutral axis from the red line, if you observe, it was initially straight. In the deformed configuration it is no longer a straight line, but it has become a curve. But the slope of that curve as per our assumption will be treated to be small. So the slope of the curve of the neutral axis as well as the deformation both are small. So these are the limitations, these are the assumptions on which our theory works. It is not very restrictive as I told you, but at the same time you must be aware that the results that you get out of this theory will have these limitations. Some of these assumptions can be corrected in more advanced theories, but as a starting point you must know this Euler-Bernoulli beam theory so that you can later read and study about the more advanced theories wherein some of these limitations will sort of get mitigated. Okay, so here again I am drawing the schematic, this time a little bit in a zoomed fashion. So this is the undeformed configuration and this is the deformed configuration. As always I will take the x to be horizontal from left to right and y to be vertical from bottom to top, right. So the neutral axis is drawn in an isolated fashion in the right diagram. So the neutral axis is drawn in red and one of these plane sections which is normal to the neutral axis is drawn in blue. So what I just said now is the following, that the neutral axis before deformation obviously everything is straight, but now after deformation the neutral axis from the straight line it is now going to become a curve. In particular if the bending moment is constant then it will become a circle, which is called pure bending. If it is not constant then it is not a circular, it is not quadratic, it could have a general form, but that part we will deal when we come to deformations. But the point is the neutral axis no longer remains straight but becomes curve, and one of our objective will be to exactly determine the equation of this curve. It will become curve depending upon the loading. We have to determine the equation of this curve, but none the same, as we found out that the Euler-Bernoulli beam theory emphasizes the following point, that if you take a section which is normal, if you take an area such that the neutral axis is normal to that area, then after deformation also that deformed area will be such that the neutral axis remains normal. So whichever area that you have considered, firstly it remains a plane area, but it simply gets tilted. Instead of being normal it becomes tilted, holding on to the fact that the perpendicularity assumption is still granted. That is, initially the blue line and the red line were perpendicular, after deformation also the blue line and the red line are perpendicular. Since the red line has become curved or it has become tilted, now to ensure the fact that the blue line remains perpendicular, the blue line will tilt. I think I will draw this once more. So the neutral axis has to become curved. That part we have argued it in details. Now if you have to enforce this condition that the angle between the plane section and the neutral axis has to remain perpendicular and the plane section itself has to remain plane, the only way you can assure all these criteria to get satisfied is that after deformation this blue line will come here such that this perpendicularity is again maintained. It remains a straight blue line, though my drawing may show that it is not remain straight, but I have corrected it now. The plane sections remain plane after deformation, they remain perpendicular to the neutral line after deformation. This is a very crucial assumption, and we will see that it is the strength of this assumption which allows us to easily derive the equations of the beam in a very nice and simple fashion. So we will return to the presentation mode now. So the undeformed neutral axis is by our definition the x axis. The deformed neutral axis will no longer be along x axis, the deformed neutral axis will be having some deformation. Again, as a matter of terminology, the deformation along the y axis will be denoted by v, the deformation along the x axis will be denoted by u. X denotes the position of a point along x direction, y denotes the position of a point along y direction, but the deformation of these two of a particular point along x direction is u along the x direction and v along the y direction. So what we basically need to find out when we are solving for the deflection of the beam is that we need to find out v as a function of x. We know that x initially corresponds to the neutral axis in the undeformed state. If you really wish to draw this curve of the neutral axis or what is called the elastic curve for the beam, then you have to determine this function v of x. That is how exactly each and every point on the neutral axis has moved up or down. But is it sufficient? Yes, it is, because the location of any arbitrary point can now be determined through this kinematics. That is, every other point which is not on the neutral axis will be in one of these blue lines, and you know, if you know how the red line has moved, by merely using the fact that the blue line has to be perpendicular to the red line and it has to remain plane, that is in the 2D view it has to remain as a straight line, you could map each point on this blue line as to where it is going. So you really don't need to map each and every point on the beam, on the solid beam, rather you need to map each and every point on the neutral axis. If you know how the neutral axis deforms, then it is sufficient. It is sufficient for you to establish how each and every particle on the beam is moving. So with that, we therefore set ourselves this objective that we will try and find out not the deformation of each and every point, but restrict ourselves to the deformation of the neutral line. If we find how each point on the neutral line is moving as a function of x, then we should be able to find how the top fiber is moving, how the bottom fiber is moving, though that is of seldom much importance. So with that groundwork, let us see what we can establish regarding the beam deformation. So as we said that the red line denotes the deformed neutral axis in this case, because it looks curvilinear. The undeformed one is obviously straight, there is nothing to draw or talk about for the undeformed configuration of the neutral line. So at a particular point the slope is theta, right, and because it is no longer straight, it will have a certain slope, and I am calling this theta. Now by definition tan theta is dv dx. Remember what we just argued in the previous slide is that the equation of this red line is v of x. I need to find out how each and every point in this red line is moving along the in the y direction, and the movement or the deformation along the y direction was symbolized as v. So the equation of this line is nothing but v of x. So therefore the slope of this line, which is tan theta by definition, is again by rules of calculus coming out to be dv dx. So the slope of any point that I take on this neutral axis is tan theta, which is in turn equal to the rate of change of v with respect to x. Now if you look at what has happened to this extreme top fiber, the extreme top fiber, what is shown in this black dotted line, was the extreme top point was lying somewhere here. Now because the top fiber is going up and it is getting tilted by an angle theta, it is getting tilted so as to ensure that the red line and the blue line remain perpendicular, right. So if it has to remain perpendicular, it has to get tilted, which in other words means that the top point of this blue line will move by a distance which is y sin theta. What is the topmost point here? The topmost point is at a location y, right. Let me draw this picture once more in my tablet. Okay, so u is minus y sin theta. Now note, we have already made the assumption that the slope of the neutral axis has to be very small. So if the slope is small, then sin theta has to be tan theta. So y sin theta can be replaced as y tan theta, and by definition tan theta is dv dx. So u is minus y dv dx. The deformation of this topmost point on a particular plane is minus y dv dx, right. So therefore we have the transverse deflection of the neutral axis. The neutral axis itself has only v deformation, it does not have, we are not accounting for any u deformation, any deformation along the axis. But because of the Euler-Bernoulli beam hypothesis, because the beam is getting deflected, plane sections which were normal to the neutral axis have caused a rotation of this plane, and because this plane has rotated from a vertical position to an angle theta, it has carried the topmost point on this blue line in it has the point which was lying at the top of this blue line has moved towards minus x by a amount of y sin theta. Okay. So with that we see that it is very clear that the topmost point is inwards, whereas the same logic you can establish that the bottom point is going outward, which is exactly what I intuitively said few slides upstream. That was in the manner that we have drawn this diagram, the upper fibers will go for a compression, whereas the lower fibers will go for a tension or an extension mode. So this is what is shown here. So the top region will go for an tension, for a compression, and the bottom region will go for a compression. So if the top region is getting compressed, that effectively means the forces are acting in the manner as shown through this arrow. If the bottom region is getting extended, then that effectively means that it is under the action of tensile forces as shown by the arrow indicated, right. Now if the bottom portion is under tension and hence under the action of tensile forces, and the top portion is under the action of compression loading, and that is shown under the arrow here, these two arrows obviously form a couple, and that couple is the effective bending moment. So this is the bending moment that we are seeing because of these two couples kept together, right. So if it is bending like what we have seen, which is concave upwards, the region above of the neutral axis will be under compression and the region below the neutral axis will be under tension. So that is our conclusion which we have found out. Neutral axis itself is not stretched, it is not compressed or elongated. There is no effective axial load along the cross section. There is no axial load, there is only transverse load, and as such the neutral axis, which we will soon see is also the centroidal axis, is going to be unstretched, whereas the top and the bottom will have an effective compressive and tensile load, and these together, since now the top part is under compression and the bottom part is under tension, you can replace them with some effective compressive forces and the effective tensile forces. These effective compressive and tensile forces are in fact going to give a bending moment, which is what we have accounted for earlier also, but I am just establishing that from a completely different perspective. Okay, let us quickly go through this slide before we end for the day today. So now we will go for the detailed relations which will establish the mathematical formulas that we require towards our calculation. So the strain, as we know, the strain due to bending, which is called as bending strain, is the derivative of this u deformation with respect to x. We already know what is u deformation. We have calculated this u deformation to be minus y del v del x, or derivative of v with respect to x. So therefore bending strain is derivative of u with respect to x, which gives us minus y d2v dx2. So bending strain is minus y d2v dx2. Therefore stress, which is E times epsilon x, will be E times y del 2v del x2 with a minus sign. Again, the reason this minus sign appears, in some books it may not appear, is because of the sign convention. So please follow that very carefully. So bending strain and bending stress is maximum at the extreme fibers farthest from the neutral axis. So if you choose y to be maximum, then you will get to see the bending stress is maximum, whether it is tensile or compressive, that depends upon the type of loading exactly. But the point is that if y is maximum, bending stress is also maximum. So that is a very nice result. Now if you integrate this integral sigma x dA, integral sigma x dA will give you E and d2v dx2 have got nothing to do with the area of cross section. It does not change with the cross sectional area. We are integrating the stress over the entire area. So the integral of this sigma, which in turn equals to Ey d2v dx2, E and d2v dx2 is constant. V is constant over the entire cross section. What is V? V is just the transverse deflection. V is not the axial deflection, right? Axial deflection between points on the cross section differ, but the transverse deflection is the same as that of the neutral axis. So if you put that factor in, you can pull E d2v dx2 outside the integral and you will be left with integral y dA. Now if there were an axial force applied to the beam, you would expect this to be non-zero, but as per our definition of beam, we know that in beam there is no axial force. So if there is no axial force, then that effectively means integral y dA has to be 0. Now integral y dA being 0 means that the section that the coordinate that we have chosen is such that the integral y dA is 0, which means that we have actually chosen the axis to be aligned with the centroidal axis. If you remember your engineering mechanics, centroidal axis will have this property that integral y dA will be 0. So our choice of x axis therefore was such that integral y dA was 0. What was our x axis? X axis was exactly aligned with the neutral axis at the undeformed configuration. And now we are seeing that the additional requirement is integral sigma dA has to be 0. Integral sigma dA has to be 0, in turn implies integral y dA has to be 0 through this relation. Integral y dA equals to 0 means that the x axis that we have chosen was actually the centroidal axis. So this is where we have proved that the neutral axis is equal to the centroidal axis that we have come. Similarly, the bending moment that does happen, bending moment, now what we have found out is, so we have found that there is a cross section, and in this cross section sigma is minus E y d2v dx2. So sigma is changing in this cross section from compressive to tension or tension to compressive, whatever you may look like. So if I draw, in fact if I draw better, so let us draw an isometric of this. Okay. So if I take a small section here, so this section is under the action of, the way I have drawn it, it's under the action of compressive load. So this compressive load, I want to find out what is the moment due to this compressive load. So the moment is definitely sigma times dA of this small area multiplied by the x axis is running through this point. So this is y, this is y. So sigma y dA is the moment due to this small strip, and if I have to calculate the moment totally, then it is sigma y dA, right, which is what I have written in my slide. So sigma y dA is the total bending moment on the cross section, that is the stress acting on the strip dA will result in a force that multiplied by y will give me the total bending moment. And now E d2v dx2 can be pulled out, and the y present within the integral will multiply the y within the stress and will lead to y square. So integral y square dA is what we have to integrate, and again if you recall your engineering mechanics, integral y square dA is the moment of inertia. About which axis? About the axis which is passing through the centroid of the cross section. So the axis is basically this. This is the axis about which I is getting calculated, right. So if you have to calculate I, the I is integral y square dA, and y square, so if I take a side view of it, this is the axis over which I want to calculate the integral, right. So with that I get my bending moment as m equals to minus ei d2v dx2. So if I combine all the relations that I have derived in this slide, sigma by y is minus e d2v dx2, which is what you read from the second bullet, and from the last bullet what you read is m by I is equals to minus e d2v dx2. So here we have the formula for bending, which is sigma by y equals to m by I is equals to minus e d2v dx2. Again, the minus in e d2v dx2 may or may not appear in different books depending upon the sign convention, but here what we have used leads us to this formulation. So this is the bending formula that will be widely used. We will use this to solve different problems in the upcoming session. For the 2 minutes that is remaining within the formal session, as well as if you want to overstay, I would like to stop here. So KECAP is asking the question, when does bending moment and shear force remain constant? If in fact both cannot remain constant, if shear force is constant, then bending moment has to change linearly. That is what we have found out. So as per our derivations, both cannot remain constant at the same time. If shear force is constant and non-zero, then you will have bending moment to be linearly changing, right. It is only under the trivial case that shear force is constant equal to 0, then you may have a bending moment equals to 0 also, but that is a trivial case, that is a case where there is no loading. It is not even worth studying that case. Okay, DCEHY is asking, in case of bending moment diagram, how can we decide the shape of the bending moment diagram? Please do not decide anything by yourself, do the calculations, find the formula, plot it. Whether it is concave or convex, the plot will decide. Okay. So don't in my way of thinking, work from first principles, derive the expression for bending moment at any cross section. Once you derive it, plot it. If you plot it, you will be able to anyway see what is the bending moment diagram. That should answer your question. BITA is asking, in neutral axis why is the bending stress 0? That is, we have already assumed that we are not going to actually load the structure. If we are not going to actually load the structure, then in the centroidal axis there cannot be any axial deformation, which is what we have concluded right now in a few minutes from now. So therefore, since the loading is such that there is no resulting axial load on the structure, the integral sigma dA has got to be 0, which effectively means that the total compressive load on one side of the cross section should be equal to the total tensile load on the other side of the cross section, right. So, and in between where the compressive load changes over to the tensile load is the neutral axis. So that effectively means that the bending stress has to be 0. JNTU is asking how to calculate shear force in case of a couple. If there is a couple, so if I guess what you are looking for is this. So in case you are having a load in the form of couple and nothing else, right, then the shear force is obviously 0, because if you take any cut section, cut the section, there is a bending moment here. If there was a shear force here, then it cannot balance, because on the other side there is no force. So you cannot have a non-zero shear force. Only thing which you can have is a bending moment here. You cannot have anything other than a bending moment. You cannot have a shear force because there are no other forces, right. So if there is only a couple, then the shear force is 0, the bending moment is constant. ITMPJP is asking, does the neutral axis face any change during bending? Yes, it faces a change. Before bending, the neutral axis is straight. During bending, it becomes curved, right? So that's what, but the length of the curve is exactly the same before and after the deformation. So the neutral axis does not change in its length, it changes its shape. From straight line, it becomes a curve. Okay, SVECAP, what is the difference between neutral layer and neutral axis? Neutral axis is the line. If you take a cross section passing through a neutral axis, that will be the neutral layer. Okay, so these terminologies are just intermittently used. DGI is asking what is obliquity. I don't know what is obliquity. If you know it, please let me know what is obliquity. Okay. Is there any possibility of SF and BM diagram will be equal in case of any loading and how, sir? SF is a force, bending moment is a moment. So even if you look at it dimensionally, they are not the same. So there is no question that shear force and bending moment can be equal. Okay. So you just using dimensional arguments, I can rule out the possibility. The other point is the slope of a bending moment diagram is equals to shear force. So if shear force is a constant value, bending moment cannot have a constant value. So therefore there is no chance that the shear force and bending moment will be same. Oh, okay, I see your question, I got it. What changes will come when the beam is further deformed from when the neutral axis forms a circle? See, when you are talking about such large deformation, when you are deforming the beam in a circular fashion, the slope obviously is very large, right? You have a slope change to be very large. Therein your simple strain to displacement formula which we have used, that is epsilon is equals to del u del x. Epsilon is, we have used this formula which is epsilon equals to del u del x. If you have a large deflection which makes the neutral axis completely go around in a circle, then this formula will not hold. Okay, if you have large deflections with resulting from a straight to a circular beam, then this strain displacement formula has to be corrected with additional terms which are in fact nonlinear, and that will get the mathematics more complicated. So if you know the strain displacement relation and how it is derived, this strain displacement relationship is applicable only for the case that the displacement is small. So under that assumption, this formula will work. So therefore, since we are using this formula, we have to incorporate the assumption that our displacements of interest and the slopes of interest are small. ACETA is asking how SF is maximum when BM is minimum. I don't think that is true. If you look back at the calculus problem, so if you have dm dx as v, so if you want to maximize m, or if you, let's say if you want to maximize, so if you look at this relation, if you wish to maximize m, then what you have to, or if you wish to find the maximum bending moment, the maximum bending moment will be found when the derivative of the bending moment is 0. dm dx, if it is 0, then the m will be maximum or minimum. That happens when the shear force is 0. So the maximum of the bending moment is corresponding to a 0 shear force condition. It is not corresponding to a maximum or minimum shear force. Similarly, maximum or minimum shear force happens when the W is 0. So maximum minimum bending moment can be analyzed very clearly if you remember this relationship, or if you can quickly derive this relationship, then you can answer your maximum minimum questions very clearly. You will find my references given. I really like this book, Timoshenko and Young, Elements of Strength of Materials. This is the one that I grew up reading. It's pretty old book, but it is quite marvelous. It is very thin, but it is very rich in its content. So I would highly recommend this book. Beer and Johnston's book is also very good. Den Hartog has 2 books on strength of materials. You can look for that. Hibbeler's book is also good. So these are the 4 books that I have kept it as a reference materials, but I would actually recommend that you go for any one book, that is enough. I think Beer and Johnston is a very standard book. You can look through it, but I will strongly encourage you to look for Timoshenko and Young also. This is slightly more difficult, but if you it will be really good if you can follow Timoshenko and Young and let's say Beer and Johnston. That should suffice. But yeah, you have to be careful when dealing with two books with different sign conventions. So hopefully if you can take care of that, the any one or two of these books should be sufficient. Okay, Rungta's question, what should be the ratio of thickness to length in order to satisfy Euler-Bernoulli beam theory? As I think this question was asked in the previous session also, the higher the or let's say the lower the ratio of thickness to length, the better is your approximation for Euler-Bernoulli theory. There is nothing like a hard and fast rule that this is the best or that is the worst, right? If you have between two situations wherein you have a thickness to length ratio, let's say of 0.1, and in another case let's say you have thickness to length ratio of 0.01. So if you have a thickness to length ratio of 0.01, the calculations which you make out of Euler-Bernoulli beam theory will be more accurate, will be more correct. That's all we can say. But yes, when is it that, let's say, even to engineering accuracy you will not have Euler-Bernoulli beam theory holding true? If it is falling below 10, if it is falling let's say the length to thickness ratio, if it is more than if it is less than 10, the length is less than 10 times the thickness, then you are asking for some trouble, and even to engineering accuracy you will not get a good estimate, not close to engineering accuracy, and therefore you should not use in such situations the Euler-Bernoulli beam theory. So I will, if you have to put a number for it, I will say thickness to length which is lesser than 0.1 is good enough, but if it is more than 0.1 you won't get engineering accuracy. Okay, so that answers the question. Okay, CIT CMB is asking what is I in the bending equation. So in the bending equation, the I over here is integral y squared dA, which is moment of inertia. Moment of inertia about the neutral axis is moment of this is the area moment of inertia of the cross section about the neutral axis. So this I is integral y squared dA, which is the moment of inertia of the area of cross section about the axis. So I hope that gets clarified. So I will encourage you to use the course website and post your questions. It has been a little fast, I agree, and within the allotted time I could not have the question answer session. So thank you for those who are overstayed and are interacting with me for the question and answer session. If you have additional questions for which you seek clarification, please post them in the course website. Take the help of your teacher if you have to post the questions. I should be able to answer that for you. So with that, we have come to a closure for today's session. Thank you very much, and we'll meet again in the next session.